Hey everyone, welcome back. This is our fourth installment of ordinary least squares regression analysis in R. If you haven't watched the previous videos, videos 1, 2, and 3, you'll want to do so before we start in on this video because it's going to make relatively little sense unless you go back and look at those previous videos. So let's just dig right back into where we left off. So it's been about a week or so since I recorded part 3 of this, so I need to change the date on our document here. Sometimes I'll make this date. There's a command that you can write to actually pull the system clock time and date, but I like to, for these kind of projects, to go on ahead and just leave the actual date manually inputted here because it reminds me of the last time that I actually dug into this project. So great, so I've changed the date on that, and I'm going to go all the way down here to the very bottom, and I'm going to run all of these previous R chunks, and so that I have it all already stuck inside of my environment. And yeah, looks like we're good to go. And then run that final one. Looks like it's still going. And we're taking some time now. We can do it. Yay. Alrighty. And there's our final graph. Fantastic. All right, so we've kind of worked on a previous kind of baseline model for our salaries data, and then we also put together a kind of a difference in means test, if you will, between the log of salary as well as our various professor ranks here broken down by gender. All right, so great. I'm going to create a new section here, and I'm going to put model 2. And let me go right back up here and grab our initial estimation for model 1 because it's kind of a good baseline model. Oh dear, we had some HTML code. Let me X out of that preview. Fantastic. All right, great. So we'll go to this previous R chunk between line 66 and 69, and then we are going to pull that information here. And actually, I'm just going to grab the first part of it. I'm not going to actually grab the actual summary. And then scroll down all the way to the bottom, and then I'm going to insert a new R chunk, and I'm going to paste that in there. And then I'll rename the first model to be second model. Great, and then we're going to add an additional component here. We're going to account for this joint variation between rank and gender. And so in order to do that, we're going to create a new variable. And this, mathematically speaking, this is all of the, this is basically a factor variable where we take this gender and we break it down, multiplying it by rank. So in order to get all of those, I'm going to use the notation of colon. So I'll type in sex for gender, and then colon and rank. Now the ordering of this does not matter. You can do rank colon sex or sex colon rank. Either one, it would give you the exact same result. But this is going to then give us the interaction between the rank variable and the gender variable relative to the initial one. So of course, where we had before, and as we saw in model 2 and again in model 3, is that we eliminated one of the groups, and so the only group that was left, I believe it was the male group that was actually estimated, but it's relative to the omitted group in that case. And so once we do that, then we have a distinctly different model here. And great, I'm going to put in a separate R chunk down here below. We use the Stargazer command, and we will go on ahead and put in both the first model object as well as the second model object. And we'll set that type equal to HTML, and we'll set digits equal to 3. And then up here inside the curly braces, we'll say we want those results to be equal to as is. That way it actually takes the HTML output from that and evaluates that HTML output. We're not going to change any of the other options within the Stargazer package. There's a whole bunch of different options. You can change how the covariates are labeled. You can change. There's all different types of customization features within the Stargazer function. I highly encourage you to look at the documentation for that. So great. So once we have that that saved and good to go, we'll knit this document and see the full output over here in the preview pane. Normally, I think by default it doesn't show up here over in the viewer pane. If you want to be able to change that as an option, you can hit this little options widget here, and you can allow the preview to be in its own separate window, or you can allow it to show up in the viewer pane. Now that only particularly works for the HTML output. A PDF is still going to come pop up in a separate window. Same thing with a Word document within the R Markdown ecosystem. All right, so we're going to scroll down this HTML document. All this should be familiar to you from the previous videos. And so here we see both of our models organized side by side, Model 1 and Model 2, and it'll take the name of the variables and line them up if they correspond. If there are additional variables, then they just show up as blank sections here. So clearly in the first model, we don't have an interaction between the rank of associate professor and male gender, nor do we have the interaction between the rank of professor and the male gender. So these two variables just don't show up in the first model, but we account for them in the second model. Now, interestingly enough, when we account for this interaction, which looks visually as if it is there, here, in the previous graph up here, it doesn't appear to be statistically significant. So while we have this outcome visually, when we actually account for the joint variation in the data, given all the other covariates, this turns out to not be statistically significant. So we can see we don't have any indicator of significance happening here, and certainly if we calculated a t-test for these coefficients, we would find them not to be statistically significant at any reasonable level. So that while that was a good idea for us to kind of follow through, it turns out that actually doesn't end up helping us all that much. Additionally, we can look at adjusted R-squared, since we are adding some parameters and some additional variables to the first model. In the second model, then we would want to look at the difference between adjusted R-squared from the first model to the second model. And remember, I said that adjusted R-squared penalizes you for including variables that are not important in the model, and we can certainly see that effect happening as we go from first model to second model. So you'll notice that adjusted R-squared actually was reduced. So the penalty for including the interactions between rank and binary gender in this case do not, it doesn't help us anymore in explaining the dependent variable salaries, but it actually ends up hitting us in terms of overall goodness of fit. So we probably want to take that out in this case, given that it's not individually significant, it's not jointly significant, then that kind of would indicate that we don't need to include that in our model. Generally, in terms of being good practitioners with econometrics, it's often frequently said, and there's a good deal of math to actually justify this, that it's better to include an irrelevant variable than to omit a relevant variable. So if you have an irrelevant variable, then that's not going to hurt you necessarily all that much. But if you fail to include something that's really, really important for you, then in that case, that ends up being problematic for you. So yeah, oh well. It was a good try, but we'll kind of take that out. So we're going to move on to our third model, our third guess in this case. And for this, I'm going to take the entire R chunk from line 112 to line 114. I'm going to copy that and paste that here. We'll relabel that third model that we're going to try. And I'm going to take out this interaction between gender and rank, but I am going to include another calculation here. So I previously mentioned that we have kind of a quadratic shape when we plot the log of salaries along with the a number of years from PhD attainment. So we plotted this, and notice we had this kind of like hump shaped here happening here. So it looks like we have some type of optimum kind of happening somewhere around, I don't know, year 30, if you will. where after that point, then salaries kind of falls off as we get further and further away from our PhD studies. So in order to kind of capture that effect, down here in Model 3, we're going to include a squared term to this. Now, if you want to square terms here, you have to be kind of careful inside of this LM function here. You don't just want to take a variable and then put caret 2 in front of that, because that would certainly denote intuitively a squared, but then that won't actually do exactly what we want it to do. So we're going to use this I function. And this I function loosely kind of represents as is. Basically, in everything inside this parentheses, I want you to mathematically calculate this and use that mathematical calculation inside of the ln function. So here we'll take the variable years since PhD, and we will square that. So here, instead of getting some type of interaction between these two variables, we want to actually square this for all values. So it's wrapped around within that as is function here. And then I'm going to take line 116 through 118, and we are going to incorporate our third model type in here. So we'll put third model. We will keep everything as is with HTML there, and I'm going to go on ahead and knit this document rather than actually previewing it, since again this is HTML and I don't want a whole bunch of HTML previews inside of this actual R Markdown environment. Well, let's go ahead and just see the actual output show up here over in our viewer pane. So great, so here we have models 1, 2, and 3. And great, so we no longer have the interactions between rank and gender. So again, it doesn't show up in model 1. Now it's not going to show up in model 3 either. But notice here we have this other variable here, the square of years since PhD. It doesn't show up in the first model, it doesn't show up in the second model, but it does show up in the third model. Also notice that the parameter value is squared. This is generally indicative of if there is a quadratic term. What you'll find here is in the first effect happening here is positive, and then the second effect being negative, which kind of indicates that your slope is increasing up to a point and then it starts to decrease after a while, so you kind of do actually imply an actual optimum value happening there. And there's a way to actually back that out too. We'll try to get to that with some more concrete examples of this. It's relatively small, so that's a really tiny effect happening there, but although one that is statistically significant. So that's at least a variable that's probably relatively important to include, and we have some justification for doing so. Finally, if we notice, again, looking at adjusted R squared, I won't go too much in terms of being able to I don't want to drive that home, that point home too finely to say R squared is the end all be all in terms of goodness of fit metrics, but it is a really good metric for being able to do model comparison back and forth against one another. So here we in the first model we had 0.517. It decreases with the interactions between rank and gender. When we exclude rank and gender, but we include this additional squared term, all of a sudden adjusted R squared does shoot up relatively more in order to account for that additional variation, despite the penalty of including the additional variable in there. Also, you'll notice here in terms of model comparison, I'll just highlight this the row for the residual standard error. This residual standard error, of course, is going to be the standard error of the actual model residuals, and so we can see that is reduced. It goes from 0.181 in both in models 1 and 2, and it reduces down to 0.179, albeit that's still a relatively small change in residual standard errors. You would clearly, if you're fitting the data better, your error terms is smaller. Each individual error is on average smaller, so that you would expect in the standard deviation of all of those error observations to be reduced in that aspect, and in this case it certainly is. Great, fantastic. All right, so that we kind of feel like we're settling in on a model that's relatively important here. I also noticed something that's kind of interesting here. So when we moved from Model 1 to Model 2, we lost some significance. So some variables that were important to our decision making, they maintained that importance, but some of them they weren't. So I take the rank of associate professor relative to assistant professor. Was statistically significant in Model 1, and then it drops out of significance in Model 2. So the inclusion of the interaction between our binary gender and the rank of associate professor relative to assistant professor, that pulls some explanatory power from the initial term, and the collinearity in that kind of it doesn't always do this, but in this particular case, it basically robbed the model of the explanatory power from that particular independent variable. Including the square of years since PhD, that's not looking to be the case. So we actually maintain significance of some of these other parameters. So it looks like we're actually coalescing around a good model. So given that, what I'd like to do is I'd like to rerun some of these plots, if you will, for our residual, some of our diagnostic plots, so that we can actually get a better idea of what's happening to these residuals. Are we kind of taking care of some of the clustering effects? So we'll use that plot function again. In this case, I want to give it third model, and then we have to specify which plot we want. So I'll start with model 1. Didn't mean to get rid of that H. All right. And I need to make sure that this guy is run and is saved in our environment, and so then I'll run that. Great. So as we look at this plot of residuals on our vertical axis and our fitted values on our horizontal axis, we do have a little bit of clustering happening here at the upper end, but a lot of the hard clustering that occurred before is kind of eliminated. Let me go over here to the viewer pane and scroll up to the initial one. Yeah, so we can see with the initial residuals plot over here from Model 1, we had a whole bunch of clustering happening, and it looks to be that we've kind of dispersed some of that. So we're able to explain more of what's happening on this end of the salary distribution, less so on the upper end. Of course, that kind of is expected because we're still not accounting for something that's inherent probably within the variation within the whole distribution of those that are full professors. So that kind of makes sense. We still have some work to go, but we're at least doing better in that regard. Let me keep on going here. We'll do a QQ plot, see if that gets any better. A little bit, but not much. We eliminate some of the variation that popped down here. We kind of have some a little bit more of the fluctuation up here is explained. So we are doing relatively better in this QQ plot. It's still not quite to normality, although that could just be a function of the actual data itself. We may never fully get a normal QQ plot that should perfectly mimic a standard normal distribution, but it does look that we're at least making progress in the right direction of that QQ plot. Finally, we will excuse me, there we go, and then we will look at the fourth one, the Cook's distance. And Cook's distance, what do we see? Before we had observations 283, 293, and 331 kind of being problematic. It looks like we at least take care of observation 293. It's no longer that much of a concern, but our big outliers are still observation 283, 331, and 351 now is kind of popping up to be at least the top three observations that are the most likely to skew the actual parameter estimates, and they do look, at least in the case of 351, it appears to be considerably different than other observations. But notice that this scale happening down here on this side, things are looking relatively better in terms of explaining the overall variation. At least with this, some of these other observations, some of these scales are much more dampened. Even though the overall distance here is still relatively high, 351 appears to be scaling that pretty considerably. All right, so overall, we're making some progress here. Even if we don't have a perfect model for this, we have something that's at least worth exploring and going forward with. So at this point, because otherwise this video is going to get incredibly long, and my videos have already been getting longer than they need to be, I'm going to cut this off now, and we're going to come back to part 5. And in part 5, I want to talk about interpretation of these parameters that we've estimated. So we're going to fully interpret all the coefficients. We're going to talk about predicted values, and we're also going to plot some two-way plots with the each given independent variable as well as the dependent variable that we're modeling, given the actual point estimates that we've estimated with our linear regression model. Thank you so much for watching, and be sure to come back next time for part 5 of this series. Take it easy, guys.